Hi everyone, my name is Chongzhou Fang. I'm a fourth-year PhD student at UC Davis. So today I'm going to talk about our paper entitled Large Language Models for Code Analysis. Do LLM really do their job? So this is the outline of today's presentation. I will first provide some brief introduction and background knowledge. Then I will give details about our experiment settings. Then I will start presenting our results and findings. And finally, I will give some concluding remarks. So I will first start with some basic concepts. So in this paper, code analysis refers to the process of analyzing code and figuring out the functionality of the code and generating explanation for the code. So as nowadays software systems are becoming larger and larger, it's important to build automatic tools to perform such tasks to assist human developers. So the second concept second important concept in software engineering is code obfuscation, which is also our focus, one of our focus today. So code obfuscation is a technique that converts a piece of code to functionally equivalent, but hard to understand. So this is an example of code obfuscation. You can see that this is a simple hello world example in JavaScript, and after some code transformation, it becomes totally confusing and unreadable. So these techniques can be used to protect intellectual property, but sometimes can also be used by malicious software writers to hide their malicious intent. So as we all know, large language models have become extremely popular nowadays. Everyone is using LLMs, and we can see there is a broad range of application scenarios for LLMs. So one promising area of applying LLM is applying LLMs to code-related tasks. Actually, there are already some commercially successful applications like Copilot and Amazon Code Whispers. But in the time of submission, a lot of the efforts are actually focused on code generation, and there aren't really a lot of thorough evaluation work on the capability of large language models to perform code analysis, especially when large language models encounter obfuscated code. So our paper provides a timely response to this matter and fills the gap of literature. So the focus of this paper is to evaluate the capability of LLMs to perform code analysis-related tasks. So I'll talk about some experiment settings. So in this research work, we aim to answer two research questions. The first one, do large language models understand code? The second one is, can large language models understand obfuscated code? So we covered a relatively wide range of state-of-the-art large language models at the time of submission. So we cover the OpenAI GPT series, which are GPT 3.5 and GPT 4, which are the most advanced commercial large language models at the time of submission. And we also deploy some smaller but still powerful models like Llama, CoLlama, and StarChat Beta. To perform our evaluation, we first construct a data set. Our data set consists of two parts. The first part is the non-obfuscated code data set. We cover 3 programming languages: C, JavaScript, and Python. These are 3 of the most popular programming languages on GitHub, and they cover low-level system programming languages to high-level script languages. The source of such code samples is shown on this slide. So this slide shows the line of code distribution of our dataset. You can see that our dataset actually covers code files ranging from only a few lines of code to extremely large code files that have over 10,000 lines of code. The second part of our dataset is the obfuscated code dataset. It also has 2 parts. The first part is built based on the JavaScript non-obfuscated code. we take out the JavaScript code we have in the non-obfuscated code dataset, and we apply some obfuscation techniques to it. And these techniques include some very basic and classic code obfuscation techniques like dead code injection and control flow threatening. It also covers some of the most advanced obfuscated method like W-obfuscator, which is a WebAssembly-based obfuscation method. So the second part of the obfuscated code dataset is a subset of the winners code samples of the International Obfuscated Code C code contest. So IOCCC is a contest that challenges participants to write the most confusing and unreadable C code. So we include the goal of including this code is this set of code is to see if LLM can deal with code that are obfuscated by very flexible and non-standard obfuscation methods. So this is the outline of our experiment. So we first collect code samples from online sources listed above, and then we remove all the comments in the code files, and then construct a non-obfuscated code dataset. And by feeding this dataset to our language models, we get some results, and by analyzing the results, we're able to answer research question 1. And by taking out the JavaScript branch of the non-obfuscated code dataset and pass the code samples to some obfuscators, we obtain some JavaScript obfuscated code samples. And combining these code samples with the IOCCC dataset, we can have an obfuscated code dataset, and we will then be able to answer research question 2. So one essential part of this research is how to figure out what is the ground truth. So we don't have explanation or analysis results already available online, and it's not enough to just extract the comments from those codes. And it will also take a great amount of human effort if we just write the code analysis results by ourselves. So we made a trade-off here. We utilize the analysis results generated by GPT-4, perform a human validation, and then we use the code samples that are marked as correct as the ground truth. So specifically, we pass all the analysis results generated by GPT-4 to several experienced programmers, which have over 5 years of programming experience, and then they will see whether or not the generated analysis results match the original functionality of those code. If yes, the code sample, the generated results will be marked as correct. So we will compare analysis results generated by other models using several metrics, cosine similarity, a BERT-based semantic similarity, and a ChatGPT-based similarity. The third one is simply prompt ChatGPT and ask if the two pieces, the two paragraphs generated by large language models describe the same piece of code. So I will present some results and important results and findings. So first, let's take a look at the validation results of GPT-4. We can see that actually GPT-4 has very good analysis accuracy. So it reaches overall around 97.5 analysis accuracy, and the analysis accuracy for all the three languages are very similar. These results indicate that GPT-4 is actually a good source of analysis, the code analysis results. It can reliably generate correct analysis to provide a source code. But we also have some other interesting findings. The first one is that we find that GPT-4 will utilize information provided in identifier names to assist code analysis. This just like human beings. So this means that if the provided code is well written, the quality of the generated analysis result will be higher, will be better. So the second finding is that we find that GPT-4 will occasionally make wrong associations. So when we look at the samples that are marked as incorrect, we find that actually in one of the analysis results of a Python script is that the Python script imports pandas, but in reality, it does not import that library. We suspect that this might be related to hallucinations, because probably in the training set of GPT-4, pandas are usually placed together with some other data analysis related libraries like NumPy and Matplotlib. And because that specific Python script imports these libraries, GPT-4 just makes wrong associations and assumes that the pandas library is imported. Okay, so let's take a look at the performance of other models. We can see that actually GPT 3.5, the performance of GPT 3.5 is also very good, very similar to GPT-4 if we look at figure C. It almost produces, it almost got every code sample correct. But if we look at the accuracy results of other models, we find that actually they don't perform well. In a lot of the cases, those smaller models simply returns the original code samples, or it returns a rewritten version of the prompted code without providing any analysis. Even after removing the returned code, the analysis results are mostly incorrect. So we have a conclusion here. Smaller models are unable to reliably generate consistent paragraphs of code analysis results. Okay, well, next we look at the performance of large language models when they are faced with obfuscated code. Because the performance of those smaller models are extremely bad, they really provide no useful information. We simply provide the results of simply ignore them and only provide results from GPT 3.5 and GPT-4. So we can see that actually, to some extent, the GPT models are able to perform code analysis tasks quite well, especially when they are faced with code that are obfuscated with only classic, so some basic and classic techniques. We can see that the first four obfuscation techniques are rather classic and basic, and we can see that the performance of those two models does not drop significantly. But when it is faced with some advanced obfuscation techniques like the W-obfuscator, which is a WebAssembly-based obfuscation method, it becomes totally unusable. So this means that LLMs fall short of when it's faced with of code that are obfuscated with some advanced obfuscation method. So we further challenge GPT models and ask them to perform some type of code generation task. We ask them to deobfuscate code and provide the deobfuscated version of the provided code. Here we feed those GPT 3.5, GPT-4 with the IOCCC code, as we mentioned in the obfuscated code dataset. So we can see that actually both models perform very poorly when they are faced with such flexible and non-standard obfuscation method. We can see that GPT-4 actually fails to generate results for around a quarter of those code samples. And most of the code samples generated cannot pass the compiler, and only 1 or 2 code samples can be successfully executed and produce the same result. The situation is quite similar for GPT-3, except that GPT 3.5 is slightly better. So we conclude that actually GPT series actually are unable to generate compilable and runnable deobfuscated code. However, it might be tempting to conclude that GPT 3.5 is a better model at this task, but by examining the generated code in detail, we find that actually GPT-4 generates more, the readability of the code generated by GPT-4 is actually better, and they provide more meaningful identifier names, and the structure of the generated code is actually clearer. So this means that GPT-4 is still a better model. And the success of GPT 3.5 probably is just due because GPT 3.5 preserved more of the original obfuscated code. So finally, the conclusion. So in this paper, actually there is an interesting case study section in this paper, and due to the time limit, I'm not able to cover it today. In that section, we evaluated the performance of GPT series models on some realistic code repositories, including some GitHub repos that are published recently, and the decompiled code of a famous ransomware called WannaCry. So if you're interested, you can read the original paper. So finally, a conclusion. So in this paper, we perform a thorough evaluation of code analysis capabilities of popular large language models. We find that those larger language models are able to perform the code analysis tasks, while smaller models are unable to do that. But even the GPT series model have some limitations, especially when they are faced with obfuscated code. So we have an online appendix on GitHub. You can access the appendix using this link. It includes our dataset and most of our results and some analysis scripts. Thank you. I'm ready to take questions.